Hello, my name is Ángeles López, and I would like to present our work, Spherical Panorama Compositing through Depth Estimation. A spherical panorama is a photograph that captures a view of 360 degrees horizontally and 180 degrees vertically. It stores a projection of the 3D world on a sphere whose center is the observer position. These images are used as resources for immersing the user in a given environment, which is known as virtual reality photography. Nowadays, there are a wide variety of consumer cameras that allow to obtain spherical panoramic images and video. Additionally, Street View provides a vast amount of spherical panoramas around the world. On the other hand, the use of depths has been proposed as an effective way to make image composition easy. Depth availability allows users to work in the 2.5D space of the image, and tasks like the insertion of partially occluded objects are automatically managed. Depth estimation from a single image has been widely studied. Some of the proposed solutions obtain relative depths by exploiting user knowledge. These methods perform an optimization process subject to a set of constraints which are extracted from user input as scribbles or points. The estimated depth values represent an ordering of depths between contiguous pixels. Therefore, these are not real distances from objects to the viewer. They are called relative depths because they mean whether a pixel is farther or closer than its neighbor. Our goal is to obtain the relative depths from a spherical panorama by taking advantage of these solutions. However, there are two main issues that prevent to directly apply these methods to spherical panoramas. First, the pixel connectivity of a spherical panorama is different than perspective images. The last column of the panorama is connected to the first column. The first row converges in an only point, zenith, and so does the last row, nadir. Second, the geometry of the projection is different. Under perspective projection, straight lines in the 3D world project as straight lines in the 2D image plane, while in general they project as curves in the spherical panorama. Such image deformations make it difficult to exploit the natural human ability to interpret perspective images. To overcome these issues, we consider in this paper three different ways to present the spherical panorama to the user. We analyze the advantages and drawbacks of each presentation for introduction of depth-related information, and we finally propose to convert the spherical panorama to a cube map representation and obtain the relative depths from each of the 6 views. However, the application of DFSI to each view of the cube map separately produces discontinuities at image boundaries when depths are stitched together to create the panorama depth map. To deal with this problem, we propose to use relative depths calculated for a given view as new constraints for depth estimation of its adjacent views, thus favoring coherence among them and consequently on the final depth map of the spherical panorama. We validate the depth maps by creating new compositions with outdoor panoramas. The user can interactively adjust the relative depth ranges to obtain the objects of interest, while occlusions are managed automatically. Although relative depths do not provide an accurate 3D model of the scene, the experiments show that they can be used to create new spherical panoramas. DFSI uses information provided by the user to estimate the depth values of every pixel in a single perspective image. We chose DFSI considering the variety of the input data as well as how easy it is for the user to provide the depth constraints. the user can introduce the following elements: points with a given depth value, pairs of points with equal depth, pairs of points with different depth, floor plane. The user draws a scribble with points in the floor plane. DFSI uses convex optimization to find a depth map subject to depth constraints. For visualization of a spherical panorama, we considered the following three methods. Panoramic view. The entire scene is displayed in a rectangular area. In this view, a large number of straight lines of the scene appear as curves in the image, for example, driveways and sidewalks. Cube map. The spherical panorama is rearranged into 6 square images, that is, the projection in 6 orthogonal directions. Spherical projection. The scene is partially displayed. To observe other parts of the scene, we have to change the view direction. This type of presentation requires interaction. We aim to analyze qualitatively the advantages and drawbacks of these presentations when users provide depth input, such as points, pairs of points, and scribbles. Let us suppose that a user wants to enter a pair of points with equal depth. Probably the presentation that is most comfortable is the spherical projection, due to the human ability to interpret perspective images. The views in the cube map would be equally comfortable, except when the points lay on different views, as they are projected under different perspectives. The most uncomfortable presentation to relate 2 points is the panoramic view, due to the distortion of the scene objects, which can be prone to error. With appropriate tools, in the spherical projection, we always see all the elements without discontinuities. However, in the cube map, even if we put the most interesting part, for example, in the front, there will still be discontinuities in some areas of the scene. In the panoramic view, the discontinuity appears in a meridian of the sphere, that is, the first and last pixels of each row are contiguous in the sphere. The main drawback of the spherical projection is partiality. It does not provide a complete view of the scene at the same time, which is usually very convenient for the user to obtain a global comprehension of the entire interaction. DFSI can be applied directly to each view of the cube map representation, but the coherence of the depths across the 6 views is not guaranteed. In this work, we propose to maintain coherence across all the views of the cube map by adding new constraints to the process. We first apply DFSI to obtain the depth map for any of the views in X or Z directions. We use +Z in our experiments. With these depth constraints, DFSI obtains a depth map for this view. Then we proceed with the +X view. In order to maintain coherence with the previous depth map, the +X view is extended 1 column in its left side, which is filled using the last column of the +Z view. We add the estimated depth of this column as additional constraints, which, together with that from the user input, allows DFSI to obtain a depth map which is coherent to +Z. For the back view, we proceed analogously by considering the last column of +X, and for the left view, we add constraints from 2 columns, last column of -Z and first column of +Z. For processing the bottom face, we extend it with 2 columns and 2 rows such that we can add additional constraints around the whole image by using depths from the previous 4 images. We process the top face proceeding analogously with the depths from the first upper rows of the 4 faces. Finally, we convert the 6 depth maps into spherical panorama, which represents distances of each pixel to the center of the spherical projection. Relative depths obtained by this process provide a depth ordering that makes sense within one panorama, but it may not when compared to another panorama. If we just merge 2 panoramas with their depth maps, the result will probably not match with the user's desire. To obtain an appropriate composition, we propose to adjust the relative depths through simple scaling and translation operations. With all depth values normalized, both operations are applied, first scaling and then translation, to every pixel in both panoramas, so that the closest pixel after adjustment is selected for the composition. Additionally, horizontal and vertical panning operations provide flexibility to the composition. Panning does not resolve artifacts, but it helps in the aesthetics of the final composition. We conclude that relative depths can be used to help to edit and combine outdoor panoramas to create new spherical panoramas. This is remarkable because we do not require specialized capture systems that obtain accurate absolute depths. We obtained satisfactory results by combining different panoramas, although we left composition with indoor panoramas as future work. We use basic compositing tools, which obtain results that seem real in a very simple way. For obtaining relative depths, there are several future research lines. Compare different strategies of depth propagation, including multiple refinement, adapt the depth estimation method to spherical coordinates, etc. For spherical panoramas, to interactively provide depth information is a bigger challenge than for perspective images. A more exhaustive study could help us to provide the user more understandable and more effective tools for this purpose.